Some of the greatest computer scientists of the 60s and 70s, Dennis Ritchie and Ken Thompson, were responsible for the Unix operating system that came out of Bell Labs in the 60s and 70s. And it ran on PDP series computers. And the motivation behind Unix was that at that time, almost all computation was batch style. In other words, you had to write a program. Typically, that program manifested itself as a long, big stack of punched cards. You then had to submit those punch cards to somebody to run the program, and then you got the results the next day. And this was a very slow form of program development, of looking at the results that you needed. So the next iteration in computing technology was around the interactive multi-user use of these large systems. The idea there was, what if we hooked up terminals, more than one terminal, to these computers, to these large computers, and instead of writing a program, punching it out on cards and doing this batch process, what if we could interactively type our program and then have it run on the computer and then get the results right there and then, an interactive way of dealing with this computer. And then, because the computers were more powerful than, say, one terminal or one user required, there could also be a multi-user aspect to this system where, on a round-robin basis, one by one, the processor would give each connected terminal some processor cycles and would then allow very quickly to shift its attention to the next task. A user would hardly even notice, because at the speed at which they were typing keys or doing other jobs, the processor by that time would be back to them and would be giving its attention to that user again. So in this round-robin kind of merry-go-round style, you could have lots of terminals, lots of users making use of the same large system. Now, this was a very profound move because it enabled computer scientists and programmers to use the computer in an easier way. And out of this environment was born Unix. In fact, Unix was an operating system that was designed to do these things. It was designed to be multi-user. It was designed to share a large computer with many people and provide an interactive means of computation. But beyond these contributions, Unix was also really valuable because it was built on a deep philosophy. And that deep philosophy, called the Unix philosophy, is something that I've written about before in Twitter threads, etc., and it's worth reading. But I'll point out one element that really made the Unix philosophy special. And that was, do one thing and do it well. Meaning that in Unix, the primary way in which data was exchanged amongst applications was text. That was the universal standard. And as long as a program accepted text as an input and produced text as an output, you could basically take small programs that did one thing well and chain them together, or what's now referred to fashionably as composability. And the composition operator on the Unix command line, the element, the syntactic element that allowed you to combine many individual small programs that did one thing well, was called the pipe. And even to this day, on Mac OS or in Linux, FreeBSD, etc., modern inheritors of the Unix philosophy, you can see this on the command line. You can, for example, use the command for typing a file, which is called cat, and then you can add a pipe. And so cat will type a file, and then you can add another little program like NL, which is a number of lines counter. So if you do cat, pipe, and NL, and after cat you provide the name of a file, it'll output that file and count all the lines and label those lines with line numbers. So one program specializes in just typing a file, another program just specializes in labeling line numbers, and you can combine the two of them. Now, NL can be combined with many other types of programs too, and similarly, cat can provide its output to many other programs as well. The rule, again, is that everything is being exchanged as text. There is one loosely coupled means by which small programs that do things well individually can be put together dynamically with many, many pipe operators to do something more sophisticated, like type a file, count the line numbers, label the line numbers, identify the odd lines, remove the odd lines, take the even lines and only give me the top 5 even lines, right? If you wanted to do something like that, anybody skilled in the Unix command line art could put that command together for you in under a minute. So why am I talking about all of this? I'm talking about all of this to draw the parallel that we now see again in computer science with the emergence of language models. What language models allow us to do is they provide a modicum of understanding, not just of free-form text, but also of technical documentation, also of API documentation. So now imagine applying the Unix philosophy as a way to dynamically create applications. And that's what this video is about using chains empowered through the use of LLMs that then dynamically tie APIs together in order to solve a problem. So there are 3 aspects that I'd like to cover here. First, an LLM is a great partner to describe a task to, and then also embed in that prompt where you're describing the task, the tools that the LLM has in order to solve the problem. So for example, you could say, you are an LLM that is a multiplier. The only 2 APIs or the only 2 functions you have are add. An add can take a number and it adds it to itself and returns the accumulated value, and run x times. And then run x times takes a function, and whatever function you pass into run x times, it'll run it as many times as the second argument to run x times specifies. So these are the only 2 things you have. Now, notice you're asking this language model to build a multiplier, but you did not provide a multiply instruction. But with LLMs, they have the good sense to figure out that by running add over and over again, you can essentially emulate a multiplication process. You can duplicate a multiplication. And in experiments that I've done, and this is about the simplest experiment you can do, very easily the LLM is able to come up with a line of code that has essentially run x times and then add whatever number you're trying to multiply, and then it runs run x times by the number you're trying to multiply the argument that you pass to add. So if you wanted to multiply 5 by 2, it'll do something like run x times add 5, 2. So run add 5 twice, accumulate the answer, and return it, which is 5 times 2, 10, same answer. Now, what this simple experiment shows you is that you can ask an LLM to piece together an algorithmic solution that requires a higher level function that does not exist in the primitives that have been given to the LLM. And the LLM can not only reason through how to combine these primitives to solve a problem, but can also understand how all of these primitives connect to each other. Which output goes where, which input feeds what argument, all of these types of things. Now imagine a more sophisticated example where you have an API that's more sophisticated, that perhaps retrieves data from somewhere and then passes that data on in the form of a data frame, and then has some charting capabilities and some other analysis capabilities in the form of, let's say, clustering algorithms and things like that. Well, once you describe all of that, and as long as you adhere to this Unix philosophy of keeping an interim data format that's kind of loosely coupled, that's not so rigid that you're likely to run into impedance mismatch problems as you connect these modules together, then you have LLMs as glue. Then you have LLMs as the descriptor of the problem that can be solved by combining individual atomic elements that are part of an API. And essentially, you have a way to seamlessly weave together an entire application using LLMs, chaining LLMs together, chaining API calls together. This is a new pattern in software engineering, where instead of the ideas from strongly typed or in programming, the idea of an interface where you're going to implement a class, but in order to implement a class, it has to implement an interface. It must at least have these things present in the class in terms of data and functionality in order for it to be a compliant class. Well, that's tightly coupled because you're having to fulfill a spec, a predefined, well-defined spec. But LLMs allow you to invoke very, very creative combinations of these loosely coupled API calls, local command line tools, and adapt data to solve a problem. And the reasoning, the order in which these sequences are applied, at least for simple problems, I have personally seen LLMs come up with good solutions, combine the component parts, and result in a full application doing something. So in many ways, this form of employment of LLMs is the next iteration, the AI version of the Unix philosophy, where simple things that do one thing well, combined this time not with pipes and the Unix command line, but combined with LLMs with some cognitive capability, really can totally change the game with software development, because the composability is dynamic and the composability and the refactoring of components is near real time. You put in another description and the whole program morphs and changes. Now, many listening to this would think, well, but how would you ever debug something like this? Again, through LLM-powered debuggers, through LLM-powered test case writers. So as this new software development paradigm is explored, there'll be best practices, there'll be lots of new techniques that'll come up, but this has such great potential that I would encourage every programmer that's intrigued by these ideas to do some work, to set up some basic tests. But LLMs as glue and LLMs as the inheritor of the Unix philosophy, in my view, have tremendous potential.